this new colloquium of the Institute. Today, we have the pleasure of having Professor Christopher Berry from University of Glasgow. He's a long colleague of mine. We know from a long time ago. Professor Berry, he did his PhD in Cambridge, the Institute of Astronomy in Cambridge with Jonathan Gell. I remember that time we had some collaborations there. I was visiting, was finishing. Then after that, he moved as a postdoc to Birmingham University, one of the also main places in gravitational waves in the UK. A lot of, and then moved to another very important place in gravitational waves, now in the US, on the other side of the Atlantic, at Northwestern University, where he was working, I think he was working out in LIGO Virgo and KAGRA collaboration. And you were back in 2021, yeah, in the middle of the pandemic, to Glasgow. Actually, Glasgow is a historical place in gravitational waves. They were already, from the instrumental point of view, and also from theory, has been a place that from the very beginnings of the field, they have very important people. They have a very large group. They have people in instrument theory, data analysis, and Christopher is now there working, and he is an expert in almost all the areas of gravitational waves, so maybe not in instrument, right? But except in this, the rest he has been working, and probably you will see in his seminar different aspects of his research. So please, you're welcome, and what you want.
Thanks very much, Carlos. It's a pleasure to be here. So yeah, as Carlos said, I was last here for a conference during my PhD, and it's one of my favourite conferences. So it's nice to be back and here today to talk a little bit about how we can learn about black holes with gravitational waves. Be concentrating mostly on the LIGO, Virgo, KAGRA science, but I'll add in a little bit of LISA-related things at the end. There's a QR code there if you would like a copy of these slides, and I'll show that again at the end. So let's get started. There we go. So what I want to talk a little bit about today is gravitational waves have opened this new window on the universe. They just introduce you a little bit to how we make observations of gravitational wave observations with gravitational waves of black holes, and how we extract the information from the signal. I know there are experts in the audience on this, but hopefully this will answer any questions anyone has been wondering, but we're shy to ask about how we do this. Over the last decade, we've really expanded what we know about black holes thanks to these gravitational wave observations, such that to really understand the astrophysics, we now use the population of sources. So I'll talk a little bit about how we do what we call population inference, using the catalogue to really start to understand the astrophysics of the sources. And from that, start to look forwards of what we can do in the future, and how the large amount of data we have is starting to pose us challenges from a theoretical point. So let's get started with an image I love to show in my undergraduate lectures on astronomy. This is a wonderful NASA image of the Milky Way across the electromagnetic spectrum. So here we have in optical, you can see the band of the galaxy, you can see the dust towards the centre here, you can see the stars. That is what we have done historically with astronomy. You look up, you see the beautiful night sky, you can learn an awful lot with it. Over the course of the 20th century, we really expanded our view of the universe across the electromagnetic spectrum, and each time we observed in a new way, we saw something. The infrared, you stop seeing the dust as an obstacle, you start seeing through it, or see it as an interesting object. You go up into the radio, you start seeing the gas, which you could have inferred was there, but it's invisible in optical, and it becomes the same. So you observe in a new way, you see new things, you see new aspects of things that you already knew. And so gravitational waves are us expanding our view further, not just relying now on the electromagnetic spectrum, but looking with gravity itself. And hopefully this is not a spoiler for anyone, but our first observation just over 10 years ago now is 1509-14, imaginatively named by the date of the observation. I still think this is possibly the most beautiful plot I've ever seen of the data from the LIGO Hanford and LIGO Livingstone, as you see, agree with each other very well, despite these detectors being on opposite sides of the continent. So this was our new way of observing the universe. We went to a huge amount of effort building these detectors, which I'm most definitely not allowed to do anything with my colleagues here, very talented to do this. We went through all this effort and we got this pattern of wiggles. Right? This is just a stretching and squeezing of space-time. This is this new way of doing astronomy. How do we go from this pattern of wiggles to actually understanding astrophysics? So that's what I'd like to tell you a little bit about to start off with. And just to catch you up, as we have been observing for 10 years, this is a very recent observation from our latest observing run, which is 25/114, which is the loudest detection published to date. And you can see a comparison here between 150914 and 25/0114. You can see that the pattern wiggles, shown in green as the template matching these, they're basically the same. These actually come from very similar sources. But in purple, you see the data. Okay, you can see this is much noisier than this. This is coming from the improvements in our detection. So over the last 10 years, we've really made this progress. We're getting larger signal to noise ratios, which allows you to make much more precise measurements of individual sources, as well as the detector sensitivity increasing, allowing you to detect more sources. So gravitational wave data analysis is really a long chain of different stages, at least in the LVK, LIGO, KAGRA context. You've got to start with collecting the data, making sure your detector's calibrated, going through data quality, checking that you understand the performance of the instrument, checking for different bits of noise. Then you've got to filter through to look for the actual signals, all very important steps, which I'm going to skip over in this talk. Other experts I know who can tell you more about that. And I will concentrate on, once we know there's a signal there, once we know that we have this interesting pattern of wiggles, how do we do the inverse problem of going from the wiggles to understand what the source is? It's what we call parameter estimation. And then given that we have a catalogue of these sources, which we know the individual properties, how do we then map that back to understanding the astrophysics of this population inference? Okay, so let's get started. Here we have the first step in understanding this pattern of wiggles, which is thanks to lots of hard work by many people doing numerical and analytical relativity. We now understand what the source should look like. So here's a numerical relativity simulation of two black holes merging, and here's the signal that they put out. You see this pattern of wiggles is very similar to the data we see. You have a long, slow in-spiral of the black holes orbiting around each other. As they orbit, they emit gravitational waves that carry away energy and angular momentum. That shrinks the orbit. As the orbit shrinks, the period decreases, so the frequency of the gravitational waves go up. They move faster, the gravity is stronger, so the gravitational wave amplitude is higher. So it's a runaway process. Eventually, they get so close together that they plunge in and merge, and we will get a dramatic freeze frame in the simulation when that happens. There we go. That gives us the peak of the signal, that's the merger, and then we have it settling down to the final black hole at the end, which is the ring down. So we have a prediction for what the signal looks like, and we can calculate what that looks like for different sets of input parameters. Change the mass ratio, you change how quickly this spirals together, you change the total mass, you scale the signal, you change the distance, you change the amplitude, you change the orientation of the binary, again, change the amplitude. The phasing. So we do have an understanding of how the signal varies with different properties, so that when we compare to the data, we can see what matches and thus what the source properties are. So here we have a plot back from the end of our first observing run, when we only had 3 detectors, and we were still a bit shy about calling things detections. So we had 15, 10, 12 was given the LVK nominal there instead of GW. It's now known as GW 15, 10, 12. But these are first 3 signals. These are the waveforms we constructed from the data. And you can see there's some diversity. 15, 9, 14, quite a short signal. We only had a few cycles, whereas 15, 12, 26, you see is much longer. This is transferring them to frequency domain. So you see this merges at lower frequencies but at higher frequencies. So from what we expect here, 15 and 9, 14 should be a higher mass source. higher mass sources, bigger black holes. Bigger black holes have a wider orbit at the point that they merge, so that's lower gravitational. Low frequencies should give you high masses. Okay, we measured the merger and ring down quite well here. That sort of is set by the properties of the final black hole, set by the total mass. You'd expect to get good constraints. 15, 12, 26, the much longer signal. Okay, so that should be lower masses. Here we get much more of the in-spiral. So we should be able to measure the particular combination of the masses that governs how quickly you go through your in-spiral, which we call the chirp mass. 15, 10, 12, somewhere in between, it's a quieter signal, so you'd expect the uncertainties to be large. So when we do now our parameter estimation and the properties, this is what we have mass 1, the larger of the two masses, and 2, the smaller one, so we can't be in this grey out region. Here we have contours showing 50% and 90% intervals. You see 15 and 914 here is higher mass, 35 solar masses of each of the components. So 36 is low masses, down here just 10 solar masses or so, and 15, 10, 12 in the middle, and see the uncertainties are much larger. So here this follows roughly a line of constant total mass. Here we have a curving banana shape, which is roughly following a line of constant chirp mass. This combination that determines how well you measure things. So this was the state of things in 01. Hopefully now we have a bit of understanding where this information comes from. And this, at the time, was quite revolutionary. Like, we knew of black holes in this mass range from X-ray binary observations. Going back to the picture of the galaxy I showed, there's bright spots in X-rays. So we knew that we had things in this. We didn't know that there'd be black holes of these masses. Some people have predicted them, but it was uncertain whether actually see them in emerging binaries. So this already was a first discovery. Not just we have black holes that emerge, black holes that are in binaries, but black holes in this mass range. So that was the state of things first observing early on. This is the state of things at the end of our second observing run. So you see we have greater diversity of black holes, going to low masses and up to much higher masses. Our first detection, which was remarkable at the time, you see is now quite a typical stuff. We also have our first binary neutron star observation all the way down here, which is awesome, but I won't say too much about because I want to talk about black holes mostly today. I will point out though that the width of this line greatly exaggerates the measurement uncertainties actually on this system. It's a very long in spiral, get the chirp mass to wonderful precision. So that's exaggerating the uncertainty. So that was the state of our second observing one, which was collated together in what we call GWTC1, first gravitational wave transient. Okay, if we bring things up to date, this is the most recent set of observations coming out from the first part of our fourth observing run, which we call O4A, and this is the state of the book. First thing to notice is we've learned that you squish everything in up at low masses, makes the neutron stars hard to see, so we stretch this out to a log scale. Still got this region forbidden by the mass ratio. This is the region where our waveforms stop really becoming reliable. But over here, we have now all our contours of our events. And I think the first thing to take away is that this plot is basically unreadable. We have so many events that all the contours are overlapping, which is a really good thing. We have so many observations now that you can stop talking about them individually. You can see that, again, this event that was exceptional is now really in the bulk. We have lots of these things with about 37 masses, and you can see that the range has increased much further. Like, we're going all the way up to components of over 100 solar masses. That, again, is quite uncertain. This is what we call intermediate mass black hole. So we've done wonderful things with gravitational wave astronomy, really accelerating. It's really a wonderful way to observe this. So we have a set of observations which look something like this when we put them all together. So that was just the bit from O4A. If we add in O1, O2, O3, we get together to get this, we have this nice graphic in blue and orange showing all the gravitational wave observations, their masses In comparison, in yellow and red are the neutron stars and black holes that we observe electromagnetically. So even though we've been observing with light, finding black holes with X-rays, for example, since the 70s, and we've only been doing gravitational wave astronomy for the last 10 years, you can really see how much easier it is to find black holes with gravitational waves. They're really hard to find electromagnetically, whereas they're your perfect gravitation. Still got a bit of catching up to do on neutron stars, radio pulsars, putting these together. But we're doing really well in getting this population. So now starting to look at this population, we can start to ask some questions about where do these black holes come from, how do they form, and understand the astrophysics of this. So there are lots of questions that we want to understand about how to get these black holes. To see them with gravitational waves, we need a binary, and we need a binary that's going to merge. So you can see the gravitational waves from it. If you've never thought about how to get this, it's actually quite difficult. You can work out how close together your black holes need to be in order to merge within the age of the universe. And then if you work out the size of the stars that must have formed those black holes, you realize they can't fit together. If they formed close enough to merge in the age of the universe, they wouldn't have formed as two stars. They would just sploosh together into one big star. So we need some mechanism that will not only form some black holes, but will form them in such a way that they get close enough together to merge in a sensible time. Now, fortunately, people are imaginative, and the universe is filled with infinite wonder, such that there are many potential ways that this can happen, but each one has associated uncertainties. So one way people quite often talk about is isolated binary evolution. Our star living on its own is actually unusual. Most stars in our universe live in binaries or higher multiples. And if you have two stars living their lives together, a more massive one will evolve faster as it evolves, as it gets towards middle age. I can emphasize a little bit here. It starts puffing up around the middle, and potentially you can get the outer layers stripped off and get mass transfer to its companion, which complicates your evolution, changes your structure of the two stars. Eventually, this can collapse down, your more massive one. Maybe there's a supernova kick that could disrupt your binary or get you later. Yes, then the secondary will continue to evolve, and potentially you can get mass transfer going the other way back. So if your mass ratio is just right, this mass transfer can shrink your binary, and that can bring you closer together. If your mass transfer is unstable, so if you transfer some mass from one star and that causes it to expand, if you'll get more mass transfer, it will expand further, you'll get a runaway process. You can maybe get what is called a common envelope. So you can get the one black hole with the core of the other star orbiting in this big fluffy envelope that's shared between them, and that gives you some viscous drag. And that can then get your objects to spiraling together such that once this envelope is ejected and you get the core collapsing down to the remnant black hole, they can be close enough together then that they're a viable gravitational process. And there's various bits of fine tuning you need in there. And the kicks, you might get a supernova to be right. You need the common envelope to be just the right efficiency. Very inefficient at circularizing, you'll end up too far apart. If you're too efficient, you'll smoosh together before you eject the envelope and again be left with a single star. So there's a whole bunch of different uncertainties associated. You might think that's maybe a bit too difficult. What if we just take a big load of stars, squish them into a small region of space and let them do their own thing? Hopefully a few of them will pair up. That's viable. People talk about this as dynamical formations. It's going to happen, say, in globular clusters, nuclear star clusters, good source. You might have a few binaries of stars formed initially, but even if you don't, every so often you're going to get interactions between stars where they can form binaries. And once you have a binary, you'll get further interactions, you'll get flybys. Those tend to harden your binary after a certain point, so drive them closer together. Often in dynamical interactions, you'll prefer to maybe exchange partners and keep the heavier objects. This again is good for gravitational sources. And after some time, you'll maybe end up with two black holes close enough together to merge. Again, there are a lot of uncertainties in this, exactly in the initial conditions of your cluster, what fraction of systems were originally in binaries, how condensed your system is. And then there are uncertainties about stellar evolution, supernova kicks, how much mass your stars lose, which are common to both channels. So there's a lot we want to learn from these systems, about these systems, that we hope to do via observation. Ideally, we would take our observations and then go, okay, yes, this comes from this channel, and we can see, in order to end up with this mass distribution, we need to have this efficiency of mass transfer. So that's the overall objective. We want to get to this uncertain astrophysics, which is very general, understanding binary evolution, very important because there's so many binary stars. How do we go from these observations? So if we look at our population here, we might make a few notice these things already. First thing to notice is that we have this range of masses, which already tells you that black holes can come in very many different types. Next thing that we maybe want to notice is the obvious thing, is that the black holes we see with gravitational waves are more massive than the ones we see in X-rays. I pointed this out. Originally, we knew the masses that things came from X-ray observations. We saw gravitational waves. Those are more massive. That was maybe predicted, but we didn't know those existed before. So first question is, why are these different? Okay, they should be the same population overall. Why do we see different mass ranges in these different probes? And this is because we need to take into account selection effects. And there are actually two different selection effects which are important here. So one is related to what systems are observable, so detector-based selection effects. And the second is evolutionary, which systems go through evolutionary phases that result. So on the gravitational wave side, we can calculate our detector-based selection effect. We can see how efficient we are at detecting different sources. We do this by simulating some signals and putting them into our detector data, running our detection pipelines on it, and then seeing the relative effectiveness of our pipelines to do this. So here's a plot showing sensitivity of our different pipelines. Yellow is more sensitive, green is less sensitive, for different points in that space. So over this range, generally, the more massive you are, the better we are at detecting these. It's a louder intrinsic signal. We can detect it further away, so you'd expect to see more sources. So we can correct for the selection effects of our gravitational waves. And we do this when we do population. So we can assume some distribution for the masses, say a parametric form or something weakly modeled, such as the spline model. We can put in all the systems we've detected. We can add in the selection effects and go, okay, given that, what is the underlying? And so these are the results following our fourth observing. This is the mass distribution. Again, you see these are with different models. You see there's some uncertainties around them, but they agree on the big picture. You can see that even though we detect these large number of sources, around about 30 solar masses, we actually have a peak at about 10 solar masses. Those are hard to detect, so we detect fewer of them, but based on the ratio of the ones we see, there are actually more sources of low mass, which makes sense. We know there are more low mass stars than high mass stars, and we see. So our peak, maybe we've got a bit of a dip. We've got another feature around about 35 solar masses here, and then we have a few sources at high masses, and this continues. Okay, so we can go back to our comparison with our X-rays. We see many more high mass gravitational wave sources. That's partially due to selection effects. When you correct for those, actually more low mass, which look more like the X-ray systems. But you can also see that we have this tail up to high masses that we still don't see in X-ray systems. So what's going on there? Okay, and this is where we need to get into the other side of selection effects, not just what you can detect, but what you expect to be there due to how these systems evolve. And this is some work I did with my former PhD student, Camille, who was at Northwestern. And we were calculating the observability of X-ray sources. So what we and gravitational. So what we have here is the redshift out to which you can detect the different sources. Here's where you can detect high mass X-ray binaries in on orange. Okay, and here's where we detect these merging gravitational wave sources. So you can see we detect the gravitational wave sources at much higher redshift, much further away than our X-rays. That's the first difference. And then you need to allow for the fact of when did the sources form. So X-ray binaries, that's sort of just a few tens of millions of years after the stars initially formed, whereas the gravitational waves, you need to go through this long process of in-spiral, which can take a really long time. So if you look at where the gravitational wave sources actually merge, that's even higher redshift. Okay. So why is that important? Well, that's important because over the age of the universe, it has evolved in chemical composition. The universe started off mostly hydrogen and helium, and then we had various generations of stars that produced the heavier elements, and those enriched the composition. So if you're looking further back in time, you're looking at lower metallicity on average for the composition of the universe. So if we can do a composition, is X-ray binaries. This is their metallicity, astronomers' metallicity of fraction of elements more massive than hydrogen and helium. These form at high metallicity compared to our gravitational wave observations, just because we're seeing things locally as opposed to further away. And why that is important is because as you increase metallicity, you change the evolution of stars, and the big thing is you change stellar winds. And here's a plot showing initial mass of a star, zero-age name sequence, versus the remnant that leaves behind. These are two different supernova prescriptions. We'll come back in a second. Each of these different coloured lines for a single star, not including any of the complications of primary evolution, but just what they end up with at different metallicities. So as you increase the metallicity for a given initial solar mass, you end up with a less massive. So it makes sense that if you're observing in X-rays things formed at high metallicity and gravitational waves formed on average lower metallicity, you'd expect the black holes from gravitational wave observations to be more massive than from X-ray observations. Work here done with my former student Mike Seven, now Adelaide Planetarium. So this fits together. There's something else we need to add in though, which is when you have an X-ray binary, you also need to take into account that has a companion star. That companion star can be less massive, whereas if you have a binary black hole system, you need two very massive stars to end up together. So when you look at the populations of these, okay, that gives you an extra evolutionary selection. So here's a population of everything which would form high mass X-ray binaries. These are in black now, the X-ray binaries that would go on to form binary black holes. And you see this selects a higher mass subpopulation of that. And then when you detection weight the two of those, that pushes you to higher masses still. So this observational difference between X-ray binaries and black holes is telling us something already about where these come from. It shows you need to account for the evolution of the stars, that these two different probes give you insights into two different subpopulations of binary stellar evolution. So there's quite a bit of rich information to get out. Okay, so that's good. We have some understanding now of where these populations come from. We know that it is generally consistent with our understanding of stars, and we actually get more information out now about where these stars are. So in a similar idea to we can go from our wiggles of gravitational wave data to understanding the source properties by matching predictions to the data. We can do something similar with the population. We can take our ensemble of detections, the masses, spins, redshift that we measure for those, and we can have predictions for what those should look like for different formation channels and see which ones match, put those together to make an inference. So here's a set of different simulations that we put together for a study, different evolutionary channels. So we have different varieties of isolated evolution that end up at merging black holes, common envelope efficiency, stable mass transfer instead of unstable common envelope, chemically homogeneous evolution where the stars spin very rapidly and that keeps them nice and tight so they don't expand so much, and dynamical formation in globular clusters and nuclear star clusters. And these are predictions for the chirp mass, mass ratio, effective inspiral spin, a particular weighting of the spins that's used to work with, and the redshift, each of these formation mechanisms, and going down here with changing one parameter common to each of these simulations, which is an assumption about the birth spin of black holes in ICE. So this is how things vary. So we can map these potentially to our observations to do this inference coming. First thing I want you to note about this, though, is that how much these distributions over. Each channel does make distinct predictions for the properties, but they are not mutually exclusive. So you can't look at your population and go, yeah, this is definitely this channel. I can put this to one side. You really do need to treat the entire population together. And if you fail to account for one channel, that's potentially going to bias your overall result because you're missing a piece of the puzzle. Okay, so we want to do this type of inference. And so we can do simulations, predict these things. The simulations are quite expensive to do. So we can only do these at discrete points in parameter space. And really, we want to do an inference over continuous ranges. So work I've been doing with my current student, Storm, who's just finishing up this year, is how to emulate the population. So we can do continuous inference. So we can do a bunch of simulations, very expensive, and then train a machine learning emulator to do the interpolation between the points. We use normalizing flows for this, which is a good machine learning technique for learning distributions. And here we have a plot showing an example of this. In the solid lines of our simulation points, the dotted lines are points that we interpolate between. You can see we can get this smooth evolution of distribution for the properties as a continuous range. And using this, we can then do the inference over continuous parameter space to infer the properties of the stars. So just as we get probability distributions for individual sources for masses, we can get individual probability distributions for the birth spin of the black holes, the efficiency of common envelope, and the branching ratio for each of the channels that we considered. This is the underlying branching ratio in this plot here, and this is the detection weighted branching ratio down here. So things to take away is from our results, we see that most binaries seem to be consistent with coming from this isolated evolution via common envelope. But then when you detection weight, actually the observed population is more an equal mix between different channels, particularly these dynamic ones. So again, you shouldn't interpret the observations we're seeing as coming from one single channel. You need to allow for the mix, otherwise you're going to get biased results. We're also seeing that the results are consistent with low burst spins for black holes. That tells you something about the angular momentum transport inside stars. We see most of our black holes have lowish spins, so that's maybe not surprising. And we prefer higher common envelope efficiencies, which again tells us something about mass travel. So quite excited to get these results out, showing that this is getting some constraining power already. This is from our third observable results here I'm showing. We've done some projections for what we expect to see in the future. And this here is showing the branching ratios as this increases with time. The true population here was the zero burst spin with branching ratios shown by the dotted line. So it's showing as you increase basically your uncertainties scale with the square root of the number of detections that you have. So our previous study was the storm was about here. We should be around about here by the end of our fourth observing run. Should be down here by the end of our early into our fifth observing run. So you can see we should be able to get some quite precise constraints on the branching ratios from the different channels and actually start to hone in on the uncertain astrophysics of these formation channels as we get more detection, which is, I think, really exciting. How far can we go? So a little while ago, work here with Sam Stevenson and Jim Bout, we did a forecast of what we could do after 1,000 detections. This is a slightly older study before we were considering the mixing of different channels. So this is assuming they're all coming from isolated evolution. So you should add on, you'll need a factor of a few thousand to be able to get to this, to account for this. And what we're showing here is the measurement uncertainty on various uncertain bits of model physics coming in. So here's the common envelope efficiency, which we've been seeing constraints on already. Here's the supernova kick. And these are two different wind prescriptions for how much mass stars lose at different evolution. Okay, so you can put these all in, see how much they vary your parameters. And this is the standard deviation you'd get after measuring 1,000 of these binaries. And the scatter here is just from simulating many potential units. You can see after we have a few thousand observations, which is time scale of a decade or so, you can get few percent level measurements on these binary evolution. So I think of this somewhat as the same sort of revolution that cosmology went through into the 90s with Kobe and so on. Uncertainties coming in of orders of magnitude, and then you get a few percent. So this is, I think, quite remarkable for understanding the properties of binary evolution, or at least it would be if I trusted our models enough to this level. This is telling you your statistical uncertainties after this many measurements. It's not showing you the systematic uncertainties from this assumes your models are correct. And are our models correct is maybe a little bit of work that we need to get on by the time we get these observations. I think it's very urgent that we do this work to get our models such that we will be able to determine. So I think that's exciting. Any students in the audience who might want to do some work, there's a lot to be done here to get these models up to scratch. Yes, let's move on now. Let's talk about something else. So that's really exciting for ground-based observations. We're getting huge numbers of detections. We've got hundreds already. We'll get hundreds in the years to come. I know one of the things that is important to people here as well is what we can do at slightly lower gravitational wave frequencies with space-based, with LISA, not 2030. So lower frequencies, of course, means bigger black holes. So we will be seeing systems with supermassive black holes, perfect for LISAs. But again, we have many uncertainties knowing where those come from, in particular how they form. So we know now that if you have a population of sources that you see, you can do a population level inference and you can constrain astrophysics. Could we do something similar with space-based detectors to understand what's going on with the massive black hole there? So a source I'm particularly interested in are extreme mass ratio inspirals. This is one stellar mass component and one supermassive, one massive component. And these are wonderful because they have such complicated trajectories. Here's an inspiral trajectory. This is motion. You see that this is much more complicated than the binaries we have of comparable masses. Right? This makes them very interesting to model. It also means that the signal is much more complicated. So that's both a good thing and a bad thing. A bad thing, much harder to predict what that should look like and actually do the analysis. But the good thing is that when you do it, it encodes a huge amount of information. So with extreme mass ratio inspirals, you get very precise individual measurements of the mass of the black hole, its spin, and so on. So this, we expect sort of a slightly different behavior when it comes to population inference. It's still going to scale with the square root of the number of detections, but that prefactor is going to be different because each MRE is individually more informative than a comparable mass. So we've been doing some work on this in Glasgow, a couple of students over the last couple of years. Again, this is ignoring all the early parts of the data analysis pipeline, not worrying about the calibrating detector or how we actually detect, but just saying, if we have a set of detections in a catalogue, what could we do in order to understand this? First thing we know we need to do is correct selection. If you don't correct for selection effects, you have a biased sample, you're not going to understand the true astrophysical distribution. So just like with LIGO, Virgo, KAGRA, if you looked at the detected population, you assume, there's loads of 35 solar mass black holes, even though the 10 solar mass are more common. We need to do the same thing with extreme mass ratio inspirals, and that's rather complicated because of the signals themselves are so complicated. It's quite a difficult problem to do. So with the student Christian here, this just a couple of years ago, we put together a way to emulate the selection effects across parameter space, which makes the problem computationally tractable. And here we have just a comparison of, we have a parameterized population model. So power law with some exponent and Gaussian component with a certain mean and width, and an overall rate. Okay, this is what you could infer with a set of observations, and in orange we are correcting for selection effects, and this is what would happen if we ignore them. You can see these parameters here describe the spin distribution. Those aren't too affected. You could measure those okay, but when it comes to the mass distribution or the overall rate, you get a huge difference if you neglect the selection. So you do want to account for selection effects. We now have code Poplar, which does this quite effectively. And so we can now start to employ this work just out with my student Shaswat, looking at what we could actually constrain with a certain number of extreme mass ratio inspirals. The number of extreme mass ratio inspirals we expect over a mission lifetime is currently quite uncertain. It's probably at least a few. It could be tens of thousands in the most optimistic models, probably more likely somewhere in the middle. So what we've simulated here is population. So here's mass of the bigger black hole, mass of the component, eccentricity distribution, spin distribution is described by various parameters over here that we see probability intervals for. In black here is the true population that we simulated. And in the different colors are what we see after a certain number of observations. So these are labeled as 10 to the 2, 10 to the 3, 10 to the 4 on the plot here. Those are the number of true astrophysical signals, not the number of detected ones. We detect about 20% of those we simulate. So in purple is what you could detect with about 20 systems. So that's quite plausible. You can see we can reconstruct the distribution of masses. You can see that there's a peak in these, get an idea that we tend towards higher spins and higher eccentricities with as few as 20 observations, which I think is quite nice. You increase that by order of magnitude, you get to green, you see this shrink down on the uncertainties quite nicely. Going to blue, you shrink even more. So over sort of this range of quite plausible detections, we can get some quite nice constraints on the underlying population of extreme mass ratio inspirals here. The shrinking with air is more perhaps more easy to see looking at these parameters describing the population. It's shrinking, getting closer to the value that we simulate. Yes, we can do the same sorts of things with extreme mass ratio inspirals as we can with LIGO, Virgo, KAGRA sources, and even given the range of uncertainty we have on how many we see, for plausible numbers, we should be able to get some pretty nice constraints telling us about the underlying population and where those come from. Okay, so I think I'll wrap up there. Summarize, gravitational waves are really the perfect tool to study compact binaries. They make it really easy to detect compared to electromagnetically, and we can measure key parameters like masses and spins. So far, from LIGO, Virgo, KAGRA, we've seen we have a family of black holes of different sizes, wonderful diversity, which is consistent with formation from a variety of formation channels. Taking these all together, right, it's not the end of the story that we've detected gravitational waves, we know they exist. This is just the beginning. We're starting to do real astrophysics and putting them all together. We can compare them to predictions for different formation channels and use them to constrain currently uncertain physics of binary evolution. We see there's probably a mix of different formation channels, and looking forward to a few years, we should be able to start pinning down the key parameters of those to some quite precision. Looking further ahead to LISA, we'll be able to do the same sort of analysis for massive black holes. So potentially in a couple more decades, we'll have a complete understanding of the entire family of black holes across the spectrum and where they come from. So thank you very much.
Thank you very much, Christopher. Questions for Christopher?
Yes, first of all, thank you for such a wonderful presentation about your work. I think all this is super inspiring to people that are getting started like me to get going. So thank you very much. Then I had a question about a couple of topics you talked about. One of them was the extreme mass ratio in spirals. And I was curious about how that correlates with when you talked about binary evolution, and that sometimes that can get a common envelope. You need to take into account the viscous drag, right? But I was wondering, how does that interact with a black hole if a black hole is technically vacuum? Because I was thinking, okay, maybe then we should take into account, for example, if you take a extreme mass ratio in spiral of a supermassive black hole, which is sitting in a highly dense stellar medium, and a stellar black hole, then does viscous drag of that stellar medium affect the black hole?
Yes, so that's a wonderful question. That's so not something I've showed in this analysis here, as this is very much cutting edge. But yes, when we did talk about how you form extreme mass ratio in spirals, so just like with the compact binaries, you have different ways of forming those. There are a variety of different ways of forming extreme mass ratios. So, bonus slides. Here's a bit of an understanding. So yes, the key problem is the same, that you need to get your big black hole and your small black hole close enough together to merge in a sensible time, and that's quite difficult in this case, not because they would started off as big fluffy stars, but just because black holes are small. So to get into the what we call the lost code regime of this black hole inspired together, it's a very small target to sort of throw your small black hole. So there are a variety of different ways of doing that. You can have scattering processes, so similar things we talked about in forming binaries, where you can have things sort of diffuse through phase space until they get close enough together and come in. Okay, that can take a long time. You can maybe get something scattered onto sort of a plunging orbit and then get scattered off at the right moment, which will also work. You can maybe get a supernova kick, which just blasts you towards the black hole at the right rates. And then the one which is sort of what we were talking about here is, what if you have a disk around your big black hole? We know many massive black holes have disks, that's where we see AGN. And these disks can actually be a good location for forming stars and then black holes. And so you can get some spiraling and you get viscous drag, and that will push you in. So that can potentially be an efficient way of kind of, those are often referred to as wet extreme mass ratio in spirals in the literature. And so that's really nice for forming. And then there's the question of, okay, if we have this thing in spiraling embedded in the disk, right, then it's not just in spiraling due to gravitational wave emission, but also due to viscous drag. So that will change your evolution. So that is expected to leave an imprint into your signal. Modeling that that's what cutting edge. And so it does look like you can potentially make some measurements of that. So that would be really nice if we could fold that into the inference as an extra input parameter of not just masses and spins, but you could have your drag. And then when you want to say try and infer fraction of the MVs coming from different formation channels, that's potentially quite important. So yeah, people are currently working on that. I think lots of people are excited that that's potentially quite informative. I think we do need to watch out that potentially there'll be a variety of different effects which can leave similar looking signals. So you need to watch out for degeneracies. That's something you can take care of in this type of population inference. It's all probabilistic. So if you have a degeneracy, that's just going to widen your uncertainties. So I don't think that's an intrinsic problem, but I think it's definitely an interesting thing to look at and forecast what that will mean.
Thank you very much.
Any questions?
You mentioned that you are doing this stellar evolution modeling, and you have a huge parameter space that you want to explore to understand actually the true evolutionary model. What do you learn from the observation that helps you for the tuning of parameters? For example, there are some events which have place scales. So, like you mentioned some of the models like but there are hierarchical merger scenarios. You also simulating those, and then how, like, what is the future step you are doing in that direction? If somebody wants.
Yeah. So I think few sort of levels to that. Yes. So there are some events which are quite informative. They have unusual parameters. What I caution against is looking at one event and then making a population level statement. And two reasons for that. One is we have a mixture of different channels. So if you see one system that's definitely from this, not from this channel, doesn't mean that that channel doesn't operate. It just doesn't explain that particular one. Could still explain pretty much all of the rest. So you need to be careful not to prune too early and throw things away. The other thing to watch out for is now that we've got hundreds of events, the possibility that one of them is a 1 in 100 noise fluctuation that's biasing our results is reasonable. So you do need to look at the entire population together to account for the fluctuations. So the hierarchical formation, the hierarchical population inference takes that all into account properly. And so that's why I think that's the best way to deal with that. But yes, you do need to have all the relevant physics. So hierarchical mergers, we didn't talk about this too much, but this is where you get a second generation black hole. So we know that you can form a black hole not just from stars collapsing, but from two black holes merging together. Okay, and the properties of the black holes you get from that merger are slightly different from your first generation. Here's a study from Chase Kimball, where we illustrating this. If this is your mass distribution of your primary black hole, your bigger black hole, right, and this is your prediction for first generation black holes, then you'd expect second generation black holes to be basically twice as big. Okay, so the higher mass systems, you'd expect you could be biased if you're trying to explain everything as coming from stars. If you don't account for these mergers, you get things wrong, and it also impacts your spins. If you start off with low spins of your black holes, the spins of your remnants are generally around about 0.7. And that's because the spin of your final black hole is set by the spins of your initial black holes plus the orbital angular momentum of the binary, and it's that orbital angular momentum. So you need to account for both your first generation and second generation black holes when making inferences. If you're doing some kind of parametric model, so just fitting things based on data, you need to account for that. So you can't fit the entire population and then say this is first generation stars. That will get you biased. But if you're doing something, as I was showing, Storm, where we're taking predictions from simulations, those automatically simulated the multiple generations. So that's folded in. So it depends on which you want. So yes, that's good too. We are probably, I think, seeing some systems that are hierarchical mergers. I didn't have time to go into this, but if we go back to this plot here showing predictions for the masses of stars, you can see here there's this region where stars are not predicted to form black holes. This is a region where we think pair instability supernovas should operate. Basically, your core of your star is really hot, it's radiation pressure supported. You get hot enough that the photons that are giving you your radiation support, gamma rays that can create positron-electron pairs. having all your photons suddenly convert to positrons and electrons when your radiation pressure supported is really bad. You lose your support, you collapse down, you get a runaway thermonuclear heating up, fusion going off, and the star will just disrupt itself. That's what's predicted, that you shouldn't form black holes in this mass range. When you look at the distributions of black holes that we infer, we see black holes in this mass range. Maybe we don't see, recent work is showing maybe there's a gap in the secondary masses, but certainly in the primary masses, there are things there. So it does look like there are certainly hierarchical mergers out there to account for. So you do need to account for that, and then how you account for it, and going back to the astrophysics, depends on the approach you do. But doing parametric stuff, you need to be more careful in making statements about the distribution overall, not just first generation stars. If you're doing the population models compared to data, then that should be included in that. In terms of things to work on, there's lots in terms of looking at the data, trying to tease out how well do these map simulations, are there other gaps in the data. On the population side, as I alluded to, we need to get our systematic uncertainties down to match our statisticals, and there's a huge amount of work there if you want to get into the theory of binary evolution.
I have a question on the low mass, and I think it's slide 16, it's the plot of the peaks. Yes. Yeah. There's a peak at 10 or so, and then it seems to fall off very, very quickly towards the low mass end. Is that a selection bias? Is that actually in the data?
Yeah, that's currently a bit uncertain. So this is really just looking at the black hole mass distribution. So we don't include the neutron stars, but we don't have that many neutron stars. So with so few neutron stars, that one makes it hard to do any population inference currently because our uncertainties are just really large. But it does look like there's some interesting things going on. So again, we go back to yes, this plot here. I showed different supernova prescriptions. It was long has been observed that in the X-rays that there's a bit of a gap between the most massive neutron stars and the least massive black holes. And to explain that, people suggested supernova mechanisms where the explosion mechanisms are different for black holes and neutron stars. As black holes collapse down, there's more massive, neutron stars blast more stuff up. That can give you a mass gap here. We now see a few things in the mass gap with gravitational waves and looking at dynamical systems in electromagnetically. So we don't look like the gap, it's really a gap, but it could be a bit of a dip. So that's potentially telling us something about the time scale of which supernova explode. So it's not one of those two extremes, but it's something intermediate. The details of that are still quite uncertain, so we need to get that number of observations up so we can get that square root in. There is interesting physics, and currently a little uncertain on the exact details. The low mass end is hard to constrain because of our selecting.
Like this, these models predict, well, if the supernova models of the evolution, they consider also that maybe there is not explosion at all, there is a direct collapse, and that happens probably a lower metallicity, and that could explain the higher mass black holes. So
yes,
it is included.
Yeah, that is included. Yeah. But it is still also currently uncertain. I think the exact nature of explodability is something which is quite difficult to model. And potentially it's actually quite fine-tuned that you can go through different regions of implosion versus explosion over quite small mass ranges. So that is again, one of the current uncertainty about the details of that, and one of the details that I hope as we get to much larger sample sizes will again be able to add to our inference models and figure out exactly when things explode and when they don't explode. But yeah, it's definitely one of the fun things that people looking at things they want to model.
Questions? I have one. So for the AMRIs, the population is a bit different, right? Because so you have the population of the primary, the big massive black hole, but for the other one, it depends on the formation mechanism. So is the formation mechanism? Are you considering different formation mechanisms in your study?
In our study, so far we've purely done the phenomenological, just modeling things as power laws, not using predictions. We of course like to get to that with using the input model so far. And I think that's an interesting question of, can we use what we see for LVK sources to inform the mass of the light object there? And again, this is where we need to account for selection effects, but not just the detector-based selection effects, but the evolution. Even if you start with the same population of stellar mass black holes, you're going to preferentially select some that become extreme mass ratio intervals or massive pairs. So working out that selection effect is something we've not figured out yet, but it's interesting future work. Yes.
So, okay. Any more questions? If not, let's thank Christopher for the presentation. So Christopher is going to be here for the day, maybe a little bit more in the morning. So if anybody wants, probably going to be in my office. Before we go for lunch, we that what can I say? I think we have to get the work. We can get maybe we can go slowly.
Please, we can.